Great. So now that we have introduced dimension reduction, we just said in this video we're going to quickly look at the dataset that we're going to be using. It is the hello world of machine learning. Whether you're doing supervised, unsupervised, or whatever it is, we're going to be using the minced dataset. We use the minced dataset, and you can find this on the Godfather Jan's website. You can find it on Jan's website. But in this case, I'll probably put a link. I'll put a link where you can easily download the better version, because this should be the original one. But some people have worked on making it better, or make it more accessible. So I'll put a link to where you can get the better version. But we'll be using the minced dataset, and this dataset is composed of three sets. We have the training set, and the training set has 50,000 images. We have the validation set. The validation set is composed of 10,000 images, and then the test set, which is composed of another 10,000 images. Someone will be asking, what type of images are these? So these images are 28 by 28 pixel images of handwritten digits, handwritten digits. So those digits are going to be in a 28 by 28 box like this. So something that's written, let's say 5 is written like that. It's handwritten in a 28 by 28. So it's 28 by 28 pixel box like that. And the box itself is a black background with the digit itself, the digit being white. The digit is white, right? So that's what we'll be using. So each image is composed of an array, a 28 by 28 grid like this, or 28 by 28 array. So let's say for that image, it's an array, right? So it's like a grid like this. Here we have 28 boxes, 28 here, because it has to be 28 by 28, right? So we have 1 box, 2, 3, so 28 boxes on this side, 28 boxes on that side, making a total of 28 by 28 times 28, which is equal to 784, is it? 8 times 8, 64, yeah, 784 boxes. So here I'm saying boxes to make it easier, but actually it's not boxes. So 784 pixels. So it's 784 pixels. This is going to be very important. I'll show you where we're going to use it. So what does each box represent? So each box, right? Each box represents the darkness. Let's just say the darkness of that image. So in each box, each box will have a number. Each box has a number in it. So this number could be, in this box, it could be 0. Oh no, I want to use this. This one could be 0, 0, 0, 0, 0, 0, all zeros. And this one here could be maybe 0.9. 0.9 and stuff like that. What do those numbers mean when you look at those numbers? So the numbers, they are floats. The numbers are floats, and what they mean is it describes how dark each pixel is. So that's what it does. It describes how dark each pixel is. For our case, we're going to say 0, because of the way they are set up. A 0 represents dark, which means it represents black, and a 1 represents white. So let me just write that down so you don't forget. 0, when a box has a value of 0, it means it is a black box, and a box that is a 1, it represents a white box. So if we are to do for this 5 here like this, because it has a black background, this box here will be black, 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 black. But wherever there is a white, like in this box here, this one would have maybe a 0.7, here maybe a 0.8, 0.6, here a 0.9, 0.6 or 0.7. So wherever there is a number, it will be, there's a bit of white in it, so it will be a bit of white. It will get closer to 1 and stuff. Otherwise, all these that have gaps, these are zeros. All of these are zeros. That's what the data set basically means. And then, apart from having these zeros and ones, there are also labels. There are also labels. So for this one, this array of 28 by 28, it has its label. What number is in there? It could be 5. So for this whole 28 by 28, it is attached to a label, which is 5. So this could be image number 20. So in another, say image number 20, its label is 5. Image number 21, it could be a 6. Its label is 6. So we have labels that are numbers between 0 to 9. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And they are represented in these 28 by 28 arrays. So let's take a look at some of the coding to get this data. So as always, we just import our libraries, the ones that we'll be using, and then here we load the data set. You can load it in whichever way you save it. This is just the way where I've loaded it, you see. And then you have your X train, Y train. This is just your we are just getting the data sets that we already have because the train set will come with the zero. The first part of the train set is going to be your X train, and then the Y train is the index 1, right? Same with validation set. The actual images themselves, we are putting them here, and then the labels of the validation set. For the test set, the actual images, or the 28 by 28, they're coming from this part here, and their labels are coming from this part here. So now we have the X train and their labels, validation set and their labels, X test and the labels. So here you can verify the shapes. As you can see, the shape of X train is 50,784. Let me explain this 784. Let's go back to where we can write. So the 784 is coming from here. So you see, this box is a 28 by 28, right? But it's difficult to store it like this. So the way it has been stored in all images in one data frame is because it has been flattened. This array has been flattened. Let me give you an example of flattening an array. So let's say we have a 2 by 2 array like this, and this number is 1, this number is 2, this number is 7, this number is 9, this number is 10. If you're flattening an array, so imagine we had 20 of these images like this, right, that are stored in 2 by 2 arrays, right? This is our image number 1. We want to store it store all images in one data frame, like this. If you want to store all images in one data frame, for it to be easy, because our machine learning model, they work best when we have one data frame, and then here we have maybe the labels. We have the labels of each and every row like that. So what you can do is we can flatten this. To fit into here. What does it mean to flatten? This 2 would then come here, 7, and then instead of having a row, we will move the row here. And then if we had another row, we would move it to be there. If we had another one, we would move it to be there. So we end up with 2, 7, 9, 10. If we had another one, going well like that. And then we'll have the label that this is number 5. If we have another image, right? If we have another image number 2, here we have 10, 6, 0, 1. When we flatten that, so this is image number 1, we've flattened it, we've made it stretch out. Image number 2 will be stretched out as well. It will be 10, then the 6, this row will then get added here like this, right? It becomes 0, 1, going on, and this is maybe image number 6. and that's image number 6 for the label. So what we're basically doing is stretching out, that's what we did here. We stretched out this 28 by 28 by flattening it. So it means we had 28 here, 28 the first row, and then the second row was added to the first row like this, and then the third row was added again at the end, and the fourth row, fifth row, for it now to just be a flattened array. And now when you calculate, if all these rows are being added like this, being flattened, it means this is going to be 28, 28, 28, 28, 28, and it's going to repeat 28 times because those are the number of rows that we have. So we're going to have 28 blocks 28 times. So 28 by 28 is going to be 784. So that's why I say this is very important, 784, because when we stretch it out, we're going to have a 1 by 784 array representing one image. And then if we get another image, flatten it, we can add it at the bottom here. Now we have a second image, and we have another image, we flatten it to add it. If we keep doing that for all the 50,000 images that we have created now a 50,000 by 784 data frame. And it's easier for us to work with data frames because we can just put our labels and then train our 50,000 wide train labels, and we can train our machine learning model. So that's exactly what happened in this code here. It happened. So if you get the actual files themselves, you can flatten them, but these ones I think they'll be flattened. So the dataset that I'll put here should be flattened and easier to work with. So yes, they're saying 50,000 images with 784 pixels stretched out. So we now have stretched out pixels like this, and then the wide train, of course, we need labels for 50,000 for it to make 50,000 rows in the X train. Validation, same thing with 10,000. Same thing for test with 10,000, and that's just it. That's pretty much it. Here we just create data frames to make it easier to work with. So we have our train index. Our train index is just going to be from 0 to length of X train, which is 50,000. Our validation, we want our validation to start after our train. So our validation is going to start from length of the train, which is 50,000. So here the index for the train index is going to be 0 to 49999, because if you know Python, it doesn't go to 50,000 exactly, it goes to one before that. So length of X train is 50,000, so it will be 0 to 50,000, but the index will be 0 to 49999. And then the range for validation index would now start at 50,000 to length of the X train plus the length of the validation. So it's going to be 50,000 plus 10,000, which is 60,000. So it's going to start from 50,000 to 59999, not 60,000. Same thing with train test index. It's just going to be the length of the X train plus validation, because we want it to be after validation. So it's going to be, we're going to start with the train, validation, and then test. So that's what we're just doing here. And then we create our indices nicely, because we want to maintain, the reason why we're doing that is we want to maintain the number. We want to know number, if we say number 265, we want to know, okay, number 265, where is it and what number is it, so that we can easily pick out if we're doing it correctly when we train our model. So cool. Here we just want to describe them. You can just go through the code itself and write maybe X train head, validation head, text head, just to see what type of numbers are coming out, to do a bit of investigation. That's good homework, right? And then here the X train, we just describe it. As you can see from the matrix itself, right, most of the numbers here, they're 0. You see the mean for the first column in that stretched out index for stretched out data frame for X train, the first column, the mean is 0, which means in the column itself there actually is only zeros, because even the minimum and the max, they're all zeros. It means in the first column it's blank, there's nothing. In the second column, blank as well, blank, 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 up to 9 blank. I don't know what's happening with 10 and such stuff like that, but here we're starting to get some numbers in the 700 and stuff, 775 columns. Certainly get a bit of numbers. That's interesting. I wonder what this number is. That will be stretched out to column number 779. That's very interesting. Anyway, right at the end, you see here, at the end, there are zeros again, because no number stretches out to the boundary of the thingy, of the stretched out array. That's very interesting. Cool. Here we just have our white train, some of the red. So the first image in the train is a 5. This one is a 0, a 4. So let's look at, here we're going to try see the image itself. We want to see, because here this is a function to just plot or draw one of the images. And if we say view digit, the function, we call the function view the first digit. View the first digit is plotting a 5, which makes sense because in white train the first image is a 5. So that is consistent. Perfect. If you want to play around with this, view the third image, the fourth image, it should be consistent. And then here we just defined one hot, and if you if you've done supervised learning, you should know one hot. So that's basically we're just getting the data set here. It's not, otherwise if we keep explaining, we're going to keep explaining each and every line of the code, but that's not the intention. Here we now have our data set, we have loaded it, and when we have loaded our data set, in the next video we are going to start on the theory of principal component analysis. So let's get into that video.